Lesson 3 in chapter 29 points. Chapter 29. Nuclear reactions, which we've been studying, include naturally occurring nuclear reactions where radioactive or unstable isotopes emit alpha or beta or gamma rays and in the process become a different element. There are also naturally occurring nuclear reactions. For example, in some concentrated deposits of uranium, there are some naturally occurring nuclear reactions that take place in which you have the transmutation, the changing into a different isotope from an original one, the giving off of radioactive particles, and the release of energy. In fact, all naturally occurring nuclear reactions would give off some energy, would be exothermic. But there's also the nuclear reactions that we can make happen in our modern experimental devices such as particle accelerators. These are probably some of the most expensive scientific toys or devices ever made. And there's one up in Fermilab to the northwest of Chicago. There are others around the country and around the world. If we look at the quick quiz, what you're supposed to be able to do is determine whether or not the numbers in the upper left of the reactants equal the numbers in the upper left of the products. So if we look at letter A in the quick quiz, 1 plus 235 means you have a total of 236 nucleons on the left side of the arrow. And then on the right, if you add up 140 plus 94 plus 1 for neutron, but do it twice, the coefficient of 2, you don't get 236. So obviously, this particular reaction, did I add that up right? No, I think this one is correct. The numbers in the upper left do add up on both sides. Notice how you would indicate multiple neutrons. Another thing you should notice, back up in equation 29.20, is you should be able to predict what is X. And we've done this before in the previous lesson, but X's nucleon number, the upper left, would have to add to 1 to give you 18, which is the sum of the nucleon numbers on the left side of the arrow. And the numbers in the bottom left must add up. So if you have 2 plus 7 or 9 in the bottom left of the left side, and something plus 1 in the bottom right, in the right-hand side, the bottom left, you can figure out what element X must be. Another thing I'd like you to see in the quick quiz is that in all three of these illustrations, whether they're actually true or not, the neutron, when it smashes into the uranium-235 or plutonium-239 nucleus, splits it into 2 daughter products and also a few neutrons. This is an example of a fission reaction, which we'll talk about in Chapter 30 in more detail. Next, just how much energy is produced in the first place? And that much energy in nuclear physics we call the value Q. Now you might remember that Q could be what you compare an equilibrium constant to. In AP chemistry, you compared K to Q to see if a reaction would go to the left or to the right to get to equilibrium. That is not what this Q means. This Q is like the Q in Q equals mc delta T. This Q is a value of energy. This is the energy that comes from the nuclear mass defect being converted into either joules of energy using E equals mc squared, or into mega electron volts when you use the conversion factor of 931.5 MeVs per nucleon. The big difference from chemistry is that in chemistry, an exothermic reaction, one that released energy to the surroundings, had a negative value of Q. In nuclear physics, when energy is produced, we give it a positive value, a positive Q value, because your mass that you start with is more than the mass than you end with. And so your nuclear mass defect is a positive value. If you don't have a positive nuclear mass defect, because your reactants have a greater mass than your products, then you do not have an exothermic reaction. You would have an endothermic reaction. That is a big difference than what you're used to in chemistry. Finally, we could calculate the threshold energy for a particle that is bombarding a large nuclide and realize that as that particle, such as an alpha particle, is traveling at a rapid speed because it's been accelerated in our particle accelerator towards a target nucleus, oftentimes that positive particle, like an alpha particle, of course, has to overcome the repulsion to another positive particle, which is the nucleus of the target. So you have to have enough speed to overcome that repulsion and enough speed to do some damage to that target nuclei in order to get something to happen. Now, some medical applications. In order to talk about medical applications, we have to talk about dosage. And there is something about dosage in the handout, which is on a separate talk and a separate handout in your folder. But of course, if you receive, either intentionally or unintentionally, a dose of radiation, certain factors are very important. Is the radiation you're receiving alpha, beta, or gamma? That makes a big difference. Is it spread out over a long period of time and it's low level? Or is it a lot of radiation all at once? That is very important. What part of the body is the radiation striking? Is it striking an appendage, or is it striking your brain or your chest? And in that regards, it also matters whether it is striking somatic cells, which are the body cells like muscle, nerve, bone, and so forth, or is it striking your reproductive cells, sperm and egg, in which case it could do genetic damage. So you should recognize that from biology that you have somatic cells, which is most of your 10 to 40 to 100 trillion cells, based upon how big you are. And then you have your genetic cells, sperm and egg. And we also have various ways of measuring radiation, various units of radiation, which I've mentioned before. For example, there's the unit of Roentgen, named after a guy with that name who discovered X-rays in the 1890s. That's one unit of radiation. We can also talk about decays per second, which is a becquerel. We can talk about a rad, where rad is an acronym for radiation absorbed dose, the amount of radiation a certain tissue in your body or a certain material might absorb. We can also talk about REMs of radiation, where REM is another acronym for Roentgen's equivalent in man. And that's one that you will hear a lot in the news and is often used in communications with the everyday public. And then we also have to keep in mind that because it matters a lot what part of your body radiation is affecting, we often multiply the radiation that you're receiving by a certain RBE, a relative biological effectiveness factor. And that would depend upon a number of things, which will be in table 29.3, which hopefully we'll see in a little bit. Again, the point is different parts of your body can tolerate different levels of radiation. Now, another thing that's important to point out is that we're all receiving radiation on a daily basis. In fact, on a moment-by-moment basis. There is background radiation in the building materials that surround you because those building materials were dug out of the earth. Drywall, concrete blocks, bricks, soil, all has levels of background radiation that you experience on a daily basis. And the food that you eat comes directly or indirectly from the stuff that grows in the ground. It has natural background radiation. Air has natural background radiations in it from very, very small levels of radioactive carbon dioxide, but even more so from radioactive fallout. When way back in the 1950s, we used to test our nuclear weapons above ground, and we created a lot of radioactive dust and pollen. Radioactive weapons are not tested anymore above ground. In fact, most countries no longer even test them below ground, though there is some evidence, even within the last couple of months, that North Korea might be doing that. Now, that level of background radiation isn't very much, though it has increased somewhat over the last 50 years. Typically, that level of background radiation is about 0.13 rems per year per person. But a lot of things figure into your background radiation that add on to that. Medical treatments and x-rays that you may have had, what your altitude or elevation above ground might have, because the higher up in the air you are, the less air there is to absorb some of the incoming radiation. So right now, your background radiation is probably closer to about 300 or so millirems, or 0.367 or so rems of radiation per year per person. We could round that up to 0.5 rems per year. Now, if you multiply that number by a factor of 10, you see a limit that the government has established for the amount of radiation a person is allowed to receive for those individuals who might be working in nuclear medicine or in the nuclear field. And where they got that number from is that 10 times the 5 rems per year, which would be 50 rems per year, that's the level of radiation where we begin to see a biological consequence. We begin to see damage to your white blood cells, which are part of your body's defense system. We begin to see this damage to your white blood cells. And so what the government has done is taken the level at which we see biological damage, and by the way, you can recover from that, and they divide that by 10 to be extra safe, and that becomes your limit. Now, at 500 rems, that's where you see what we call an LD50, a lethal dose at which 50% of your population would die. And there's a lot of interesting research that's been done because of the people that have been exposed to Chernobyl. And a famous movie's been made that's on Netflix now that's about that. The point being that this is an easy way to remember these values. 0.5 for a high-end average for a person due to natural causes and medical treatments. 5, which is the government limit, at least in the United States. 50, which is where we begin to see an effect, biological effect. And then 500, the lethal dose at which you would expect a population of 50% to be affected and killed. Now, how do we gather data like this? Well, we have the studies done after World War II and Hiroshima and Nagasaki, the two atomic bombs dropped there. We have some data from biological tests. We have some very little data to very small populations of one or several or a few more individuals who might have experienced, for some reason, a large dose of radiation. And then, of course, you've got it from people that are experiencing and undergo medical treatments. Now, radiation, though, has positive uses as well. We can use it to sterilize equipment because it kills microorganisms and bacteria and viruses, though viruses aren't necessarily living organisms, though they're made out of protein and some genetic material. It can even kill worms. And so a lot of times, once you package your food, you can irradiate it with radiation, and it'll kill the microorganisms and the worms and so forth. Now, there is a little bit of degradation to the vitamin content of some foods, but the nice thing about irradiating food after it's been sealed and killing anything that might cause it to spoil is now you don't need chemicals to preserve it, or salts to preserve it, or refrigeration to preserve it, and it can last quite a long time. Now, in the United States, we are tolerating or accepting as a public more and more foods that are irradiated. We already do it with vegetables and fruits to some extent. Some of this is now done with meat, and we're not ready to do it with milk in this country, but it is done with milk over in Europe. Another use is as a tracer in anything with complicated plumbing, whether it be the human body and its circulatory system, or the plumbing of a nuclear reactor, or maybe we want to talk about the plumbing of trees that have vascular tissue that transport food down from the leaves as a result of photosynthesis, and water and minerals up from the roots. You can trace where these things go by putting radioactive isotopes of whatever metal or substance that you're trying to study and follow where they go in that living system. For example, different organs in the human body have a tendency to concentrate different elements. The thyroid concentrates iodine. So if you had a radioactive isotope of iodine, very low level, you could put that into the human body and see where that iodine goes. It would concentrate in the thyroid, and you would be able to image the thyroid to see if there's some damage to the thyroid or if the thyroid has a cancer or something like that. After Chernobyl, in a communist government, tragically, where everything is about the state and not the individual, Russia did not report that they had this meltdown at Chernobyl. And as a result, a tremendous amount of radioactive steam from the meltdown was released and drifted downwind. A lot of it fell on grasslands where cows were eating, and the cows produced milk that had high levels of radioactive iodine, which children drank in particular because they're most affected because they have very active thyroid glands, because thyroid produces thyroxine, which regulates body metabolism. And so in 10 or 20 years after the event, many children who were now adults were coming down with thyroid cancers. And this could all have been prevented if this had been reported immediately and we could have flown in easily potassium iodide tablets for the children to take. It would saturate their thyroids with good iodine. They would not have taken up then the radioactive iodine. But again, in a communist system of government, it's all about the state looking good and always being right, and you sacrifice individuals for the state. Here's another example of magnetic resonance imaging, a very common practice now that when it was first introduced and was called nuclear magnetic resonance imaging, lots of people did not want to get this done because of the word nuclear. So they literally just took off the nuclear part on the signs, and everybody is very comfortable with getting magnetic resonance imaging devices, which is all about these nuclei flipping between two different spin states under the influence of these super strong magnets as they change. And as a result of these nuclei, that's where the word nuclear magnetic resonance imaging comes from, you're able to image soft tissue, not just bones, which is all X-rays are good for. Another example is to deliver a radioactive dose to a cancerous site in the body and hope that the radiation from the delivered radioactive source will kill more cancer cells than good cells. Now, one technology that has been looked at a long time ago, it was dropped in the United States, picked up in Japan, and is being looked at again, is called boron neutron capture therapy. And this is for certain inoperable brain tumors. And what you do is you introduce boron radioactive, you introduce a boron cocktail into the body. You would drink it. This boron would concentrate in the intracranial tumor, and then you could apply some neutron beam, and it would cause the boron to become radioactive, and it would very specifically kill the radiation from the radiated boron, would very specifically kill the cancerous cells. That's the end of this video.